Chapter 11.1 is on sequences. Now, what is a sequence? A sequence is any list of numbers in some sort of definite order. So this right here below is an example of a sequence. In a sequence, because it's in order, there is always a definite first term, which we call a sub 1, a second term, a sub 2, a third term, a sub 3, and these are all very definitely defined because the order must be fixed in place. So therefore, there is also, if this keeps on going, we also have what we call a general term. And the general term will tell me a sub n. If I were to plug it into this general term, I would be able to determine, for example, a sub 21, the 21st term, or the 99th term, for however long it goes. So what is a sub n? Well, if I compare, the number on top in the numerator seems to be match up with the n, right? So on top would be n. The denominator seems to be relative to the position. It seems to be n plus 1, n plus 1, n plus 1, right? So the general term would look like this for this particular sequence. Now the general term is nice because, once again, if I were to look for example, the 99th term, I don't have to continually list it until the 99th term. I could just plug it in. So this would be 99 over 100 would be the 99th term, right? So when you have a sequence like this, this is usually what's the hardest to find. Chapter 11.1 is on sequences. Now, what is a sequence? A sequence is any list of numbers in some sort of definite order. Okay, so it's got to be in order, which means this is a sequence, and this order is locked into place. It's not just a set of numbers, they're in a definite order, which means this 1/2 must be the first term, which we label a sub 1. The second 2/3 must be a sub 2. This one's a sub 3. And a sub 4, and so forth. Right? And this can keep going forever and ever and ever, for as long as possible. We can have infinite sequences, we can have a sequence of 10 terms, we can have a sequence of 100 terms, whatever that might be. Now, we also have something that we call a general term. Right? And that is your a sub n. If I asked you, in this sequence, can you find the 118th term? Can you find that without having to list all of them in order? Well, that a sub n, it'll be a sub 118, for example. So what will that look like? Well, in accordance to this sequence, the first term, the numerator of the first term, matches up with the term number itself. So the numerator here is 3 for the third term. The numerator is 5 for the fifth term, 6 for the sixth term. So for the nth term, the numerator would be n. In the denominator, it looks like, relative to the position, the denominator is 1 more than the term number, right? So the denominator would be n plus 1, right? So this is what we would consider the general term. Now, the general term is nice because now I can find, for example, if I find this formula really nicely, I can find the 118th term. This would be n 118th over 119, right? So that's really nice. Let's look at this second example. So the second sequence, this is the order, and these are all definite orders again. So once again, this would become the first term, this would be the second term, this would be the third term, and these are all very much fixed. Fourth term and fifth term, right? So now our goal is, what is the general term? Right? And the general term is a sub n. If I were to ask you to find, in this case it's a little more difficult to see, if I were to ask you to find the 99th term, do you have to list all 99 in order to find it? Okay, hopefully not. So let's take a look here. It looks like the numerator is progressing by 1 and alternating in terms of its positive or negative. So the positive or negative is a multiple of -1, right? So the first one, when I plug in the first, it should be to the first power, will be a negative, which I don't want. I want this to have a positive exponent, an even exponent, so that it becomes positive. So you can either add 1 or -1. So now when we plug in n equals 1, 1 minus 1 is 0, and -1 to the 0 power is 1, positive 1. If I plug in n equals 2, 2 minus 1 is 1, and -1 to the first power is negative. Therefore, I have my alternating positive, negative, positive, negative, positive, and so forth. So now let's talk about our numerator. Our numerator is increasing by 1, but it starts with 3. So relative to the position, it's 2 more than the position. 2 more than the position, 2 more than the position. So 3 plus 2 is 5, 4 plus 2 is 6, 5 plus 2 is 7. Therefore, the numerator has n plus 2, is n plus 2. Now, in the denominator, if you notice, is 5, 25, 125, 625, 3125. Do you notice how these numbers look? These numbers are actually exponential. So we have 5 to the first power, 5 to the second power, 5 to the third power, 5 to the fourth power. Now, they all have a base of 5, and they all seem to have the exponent equal to the position number. So this is 5 squared, which is the position number, 5 cubed, which is the position number. So this is 5 to the nth power. All right? So this would be the general term for this particular sequence. Now let's take a look at whether a sequence converges or diverges. So we're going to take a look at this sequence once again. Now, what does it look like? Well, let's take a look at what this would look like if I were to plot this sequence. So the first term is going to be 1/2. I'm going to plot that as my first term. The second term is going to be 2/3. So these are points that I will be graphing on a line. The third term on a graph, third term is 3/4. Fourth term is going to be 4/5. And if I plot them, so forth and so forth. And if I plot them on a graph, it looks something like this. So the first term is 1/2, then 2/3, 3/4, 4/5. And if you take a look, as the sequence gets, as n reaches infinity, do you see how the limit as n reaches infinity actually reaches a certain number, a very definite number, and it looks like it's approaching 1. Okay? And if the limit of the sequence, so if the limit of the sequence, a sub n, as n gets really, really big, as I keep going in this sequence, reaches infinity, actually approaches a number, a limit, then this is a convergent sequence. This is what we call a convergent sequence. And then, of course, if as n goes to infinity of some sequence, it just keeps going and going and going, bigger and bigger and bigger and bigger, or shrinking smaller and smaller and smaller and smaller, and the limit doesn't actually approach a limit, then this is what we call a divergent sequence. Okay? Which means in order to determine whether a sequence is convergent or divergent, we have to remember all our limit laws, right? To determine whether this formula, this function that represents the sequence, to see whether that actually approaches a limit or not. So let's try an example. So example 1, it says to write the first 5 terms of the sequence a sub n is equal to n over square root of 10 plus n. Now again, once again, this represents technically a kind of an infinite sequence right now. So it's just a list of numbers. And then you have to determine if the sequence converges or diverges. So if I were to write the sequence, I would start by plugging in a sub 1. The first term would be a sub 1. So the sequence would look like this, right? A sub 2, a sub 3, a sub 4, a sub 5, magically change colors, and that it would technically keep going, but we only want the first 5. So a sub 1 would be when n is 1, so it'd be 1 over square root of 11. The second one would be 2 over square root of 12. Third one will be 3 over square root of 13, 4 over square root of 14, 5 over square root of 15, etc., etc. Right? Now, in order to see if these numbers actually reach a limit, I'm just going to take the limit as n approaches infinity of a sub n, or the limit as n approaches infinity of n over the square root of 10 plus n. Now, if you recall back to chapter 2, how do we find this? Technically, we divided top and bottom. We divided the numerator and the denominator by n, the highest degree, and saw that the limit as n approaches infinity of 1 over n is a 0. But what I'm going to do is I'm going to say this is the same thing. This has a exponent of n to the 1. This 10, as n gets really, really big, this 10 will become insignificant. So this is really like the square root of n. Right? So if the numerator, this power is bigger than the denominator, we will say this limit actually approaches infinity because the numerator grows faster than the denominator. Therefore, this sequence is diverges. Right? So again, this is for polynomials, and that's what we have here. Let's try another one. Example 2 is the sequence a sub n is equal to ln over n convergent or divergent? Now, once again, in order to do this, I want to make sure that I find the limit as n approaches infinity. So I can list out all of them. So it'll be ln of n over 1. ln of 1 over 1 is the first term. ln of 2 over 2 is the second term. ln of 3 over 3 is the third term. But is that actually converging to one number, or is it getting bigger and bigger or smaller and smaller? So we're taking the limit of the ln of the sequence, the general term of the sequence. Now, how did we find this? We cannot, this is not a polynomial or a rational function. This, however, as n gets really big, approaches infinity, and this, as n gets really big, also approaches infinity. Therefore, what can I do but L'Hopital's rule? Which means I'm still taking the limit, but I can take the limit of their slopes now. So the slope of the top compared to the slope of the bottom. So the derivative of natural log of n is 1 over n. The derivative of n is 1. So now I'm just finding the limit as n approaches infinity of 1 over n. And as n gets really big, this approaches 0. So this actually converges. This sequence converges to 0. So if we take a look at what that looks like, it looks like this. So the function natural log of x over x in this case, because I have to use x, increases a little bit, and then it looks like it starts to decrease. And as I pull it closer and closer to infinity, you can see that the function itself starts getting closer and closer to 0. So that sequence of numbers converges to 0. Now, because we're running out of time here, I'm actually going to ask you to take a look at this sequence. A sub n is equal to negative 1 to the nth power over n. See if it converges or diverges. And this sequence here, a sub n is equal to sine of pi over n, and see if that converges or diverges. Show your work on your notes. Bring it back to class, and the answers you will find in your textbook. So these are examples 8 and 9 from your textbook. So figure this one out and bring it back to class. That's it.